In this section, we're going to look at level curves. Now we have a three-dimensional surface here. Z is equal to f of x, y. And we're going to cut into it, if you will, with a horizontal plane where z is equal to a constant. And when we do that, there's a curve that the plane would form, right, as it cuts into it. That's called the contour curve. It's on the surface itself. And then we project down the shadow of that contour curve onto the xy plane, and that creates a level curve. And that's on the plane itself. And then when we graph a bunch of different level curves on the surface, we're getting a two-dimensional representation of a three-dimensional surface. Very much akin to topographical maps, if you've ever seen those. Because the planet, of course, has hills and valleys and things like this. And so when we graph level curves, what we're graphing is an image of the contour curve, right, onto a two-dimensional surface, the plane. So this contour curve is creating that level curve. Similarly, this contour curve that I can see kind of poking its head out right there, and it goes back around, is this contour curve, or excuse me, level curve, right? When we put it down onto the XY plane, it's a level curve. And for the record, it doesn't actually have to be the XY plane. You can kind of project these into any plane, but most often we project into the XY plane. Okay, now what's happening? If these horizontal planes z equals c are evenly spaced out, then the more closely packed in the rings are, or curves are, the steeper the surface must have been. Because if these horizontal values are evenly spaced, but they're tighter packed, it means that it was climbing more steeply, right? So for example, it's climbing more steeply here towards the top than it was down here, right, as it kind of flattens out. All right, so let's practice finding a level curve and drawing it for ourselves. All right, so we're going to sketch the level curves for the function f of xy equals 12 x squared plus y squared. Actually, before I go do that, I just wanted you guys to see what this kind of looks like. So I have a different surface than what we were looking at originally, but you can see that you take the surface and you're going to kind of cut into it with these horizontal planes. And when you do that, it forms these green rings. And then if you imagine casting their shadows down onto the XY plane, it would form those curves. And the example we're about to do, we're actually going to go backwards. We're going to figure out the curves and the rings first, although we can get a sense of what it looks like right here. So that's what the object looks like. Looks, I don't know, sort of like a volcano, a very steep volcano, very tall volcano. All right, so let's get a sense of that. All right, we are going to sketch the level curves for the function 12 over x squared plus y squared. Comment on the shape of the surface on what your level curves look like, based on what your level curves look like. All right, so the first thing I'm going to do is I'm going to set it equal to 12, or excuse me, set it equal to 1 and then solve. So 1 second. There, I had to get a pen. Okay, so 12 over x squared plus y squared equals 1, right? Because this is z equals, and we're going to set z equal to 1. All right, so then that would mean x squared plus y squared, because I'm going to multiply both sides by this denominator. So that would mean x squared plus y squared equals 12. And we know what that is. That's a circle. That's a circle centered at the origin with radius equal to the square root of 12, which is about 3.46. Okay, so if I go down here, I can make a circle with a radius of about 3.46. I'm just going to kind of make a little note of where I want it to be intersecting the axes with. 3.46, 3.46, something like this. Good enough. Close enough. It's meant to be a circle. All right, now what if we set it equal to 2? So we say, okay, 12 over x squared plus y squared equals 2. That would mean if I multiply both sides by the x squared plus y squared and divide by the 2, that means x squared plus y squared equals 6. So that's a circle with the radius equal to the square root of 6, which is about 2.5. So I'm going to put another ring in at 2.5. Lovely. Okay, so then we're going to do it again at 3. I think we're only going to do 3 and 4. I'm not going to do all of these. All right, so 12 over x squared plus y squared equals 3. That would mean that x squared plus y squared is equal to 12 divided by 3, which is 4. So that's a circle with radius equal to the square root of 4, which is 2. So then I'm going to have it touch at 2 right here. Now you'll notice that ring I'm drawing right now is closer to the last one than the previous one was, which means the graph is getting steeper. Right? These are really close together, the pink and the light blue ring. All right, so let's do another one. If 12 over x squared plus y squared equals 4, that would mean x squared plus y squared is equal to 3, which is a circle of radius the square root of 3, which is about 1.7 or so. So you'll notice the first ones were almost a full point apart. These are only a half point apart. These are only 0.3 points apart, right? So it's getting closer and closer to each other. So let me think, 1.7 is about there. So I'm going to draw my circle. Okay, so what's actually happening? If we imagine our three-dimensional object here, I'm not going to draw the axis. All right, so then it had a ring kind of at z equals 1. Right? This was z equals 1, and then it kind of was going up and shooting up like a volcano, right? And so we had another ring at z equals 2, and then we had another ring at z equals 3, right? Because it was forming circles, and then another ring at z equals 4, like that. So it's sort of looking like a volcano, right? A really tall volcano. And we're just seeing some of the rings. Okay, so these are the 2D level curves. And this is the 3D graph with the contour curves. Now let's look at this in Maple a little bit so we can get a sense of this. So I graphed it both with an implicit plot, which is z equals, and then I just graphed it with plot 3D, which is when you take away the z equals and just write the function part, but it has to be in z equals form. So I did that, and I've got my curve, and you can see it's this very tall pillar. So then I just wanted to look at the contours. So I did a contour plot 3D, and you can see just the rings that you're seeing on the graph itself, right? I did style, though the reason I'm seeing the rings is because I did surface contour, and so that lets you see the contour curves as you graph. And then I graphed the contour plot. The contour plot actually shows the contours. So we can see those are the 4 contour rings that we drew on our paper. There they are. Just like that. So in the regular plot, using style equals surface contour shows you the contour plots, or the contour curves, I should say. And then this one was nothing but contour plot, right? So you can see those, right? Contour plot 3D is a 3-dimensional, contour plot, regular contour plot is a 2-dimensional graph. And you might be wondering, why is this so important? Well, because it's actually the topographical map piece of this is very key to compression, right? We're compressing a 3-dimensional object into a 2-dimensional graph. That's key, right? That means less data, less everything. So that's nice. Now let's see if we can take this idea and match. Let's see which ones we can go with which. Okay, so we're going to match each surface to the appropriate set of level curves. And you can kind of do this either direction. I think some of them are easier than others. For example, this one has a really steep piece and a really shallow piece. And so does this one, right? So those are going to be either A or C. It's just a question of which one's which. So you have to think, all right, the shallow piece is over here on the positive x side, right? And y is going from negative to positive. So that means this is graph C right here. It's the same graph right here, right? Steep part is on the negative x side, which is right here. So then this other one has the shallow part on the positive y side, which is A, graph A, right? So it's got the shallow bit and then the steep bit. All right, so that's done. This one should be really easy. This one is circles, right? So it's D, right? Everything is even. That's the thing about a cone, right? Because the spacing is all even, the increase is all even, so everything would be concentric circles. So that is that level curve, right? The level curve for that graph. All right, what about the others? Well, this one, if we cut into this with horizontal planes, would be ellipses, right? Because it's forming kind of an ellipse. So that's that one. Right? All right, so what does that leave us with? That leaves us with this one that looks like a folded piece of paper. So you have to think, if I cut into this with horizontal planes, what would it look like? Well, they'd be lines, right? Lines going from negative x to positive x, horizontal lines, which is that graph right there. So this one's B. And then the most interesting one, in my opinion, this is a saddle shape, right? The hyperboloid shape. It looks like a Pringle chip, right? So that actually has a contour curve that's very interesting. It looks like this, right? Because it has steepness going down one direction and then going up the other direction, right? So that is graph E. There we go. So it goes B, E, C, D, A, F.